Neha. I'm a PhD student at the Indian Institute of Science, and today I'm going to talk about Sigma, Secure GPT Inference with Function Secret Sharing. This is joint work with Kanav Gupta, Ananta Mukherjee, Nishan Chandran, Divya Gupta, Anshish Pangar, and Rahul Sharma. And this is also the first time I'm giving a talk without memorizing it, so I want to apologize in advance for whatever will ensue. Okay. How did we do with this? How does this go forward? Yeah. Oh, this doesn't can. Yeah. Okay, great. Okay. So large language models have proved to be very successful at solving a number of natural language tasks. Large language models are, of course, mostly based on transformers, and their success has prompted AI companies to train transformer-like models and deploy them to solve problems in various scenarios and expose these models to clients. Now, unfortunately, this entire paradigm of predication as a service raises privacy concerns for the clients as well as the AI company. And in order to protect the privacy of the client as well as the AI company, we need secure inference, right? Secure inference allows secure inference via the cryptographic technique of secure two-party computation allows us to both protect the privacy of the client's query as well as the weights of the proprietary model that are held by the AI company. Okay. I'm not going to elaborate on this because I think that we already gave an excellent introduction. So let me directly start by talking about a security model, which is semi-honest 2PC with pre-processing. This is also the security model of our baseline cryptet. In this model, there are two phases. First, there is a pre-processing phase in which a trusted dealer hands out input-independent correlated randomness to the two parties who wish to securely compute a function f. Then, in the online phase, once inputs arrive, the parties use this correlated randomness and interact with each other in order to securely compute f, and focus in this model is on making the online phase fast. Okay, so now that I've established our security model and the baseline, let me talk about our results. We are up to 19 times faster and 10 times more communication efficient than Crypt10. Concretely, on GPT-2, Crypt10 takes 20 seconds to produce a single token, where Sigma takes less than 2 seconds. And Crypt10 communicates 8 GB of data, where Sigma communicates less than 1 GB of data. And I should mention here that both Crypt10 and Sigma have their computation accelerated with GPUs. Sigma is also the first secure inference system to scale to models with tens of billions of parameters. And our efficiency and our scale is made possible by the fact that we come up with sufficiently precise yet extremely efficient approximations for the complex nonlinearities that are typically seen in transformers. In fact, our approximations are so precise that we don't need to change the architecture of the underlying model at all under secure inference. And we don't even need to change model weights. And what I mean by this is that you can pick up model weights that are generated by any floating point training algorithm and use them with Sigma under fixed point and be assured that the accuracy under secure inference is going to match accuracy under plaintext. So this makes Sigma incredibly simple and easy to deploy. Okay. So now, I've talked about how Sigma provides efficient approximations of complex nonlinearities. So let me describe what these nonlinearities are. And in order to do that, I will start by talking about the architecture of a transformer. So this is the architecture of a single transformer block. And a transformer consists of several blocks that are stacked on top of each other. And as all machine learning models do, this transformer block consists of linear layers and non-linear layers. The linear layers in this case are matrix multiplications, and we know how to perform matrix multiplication securely in the pre-processing model very, very efficiently via Beaver triples. As in convolutional neural networks, the non-linear layers are the key performance bottleneck in transformers as well. And this is because they require us to compute complex elementary functions like the negative exponential and the inverse. There are three key nonlinear layers that we need to compute in transformers: Galo, softmax, and nanome. As you can see from the analytical expressions of these layers, they require us to compute complicated elementary functions. Softmax, for example, requires us to compute the negative exponential and the inverse in order to accomplish the division, and nanome requires us to compute the reciprocal square root. Okay, and because these complex nonlinear functions are difficult, they are expensive to compute cryptographically, secure inference systems, right, that want to compute these nonlinear functions end up spending a lot of time on them, right? So, for example, Crypt10 on GPT-Neo spends 20 seconds computing JIT. In Sigma, thus, in order to reduce the overhead of computing these complex nonlinearities, we design approximations for them that are efficient to compute but are at the same time are precise enough to match the accuracy of plain text, of the plain text transformer model. Okay? So now let me talk about how we approximate nonlinearities with Sigma. We use function secret cherry. And the key primitive that we use, the key FSS primitive that we use is the distributed point function. We have talked about the distributed comparison function, and the point function is very close. So it allows two parties to securely compute this function f that takes the value beta when x is equal to alpha and is 0 otherwise. And on top of DPF, we additionally build two key functionalities that we need to realize our nonlinear approximation securely. The first of these is comparison on n-bit inputs with a 1-bit output, right? And this can be built from a DPF, and this requires about n-6 AES calls for an n-bit input. And we require lookup tables, and an n-bit lookup table that is built from DPF requires about 2 to the n-6 AES calls. Because DPFs are very, very close in structure to DCFs, we are able to use forecast techniques to accelerate DCFs on the GPU, to accelerate DPFs on the GPU as well. And another contribution of Sigma is that it gives protocols that are specific to the hardware on which they are being run, right? So different hardware has different limitations, right? As Divya already said, if you run FSS on the CPU, you spend most of your time doing all FSS computation. Thus, if we know that we are designing a protocol that's going to be run on the CPU, we try to reduce FSS computation as much as we can. However, on the GPU, the constraints are slightly different, right? Compute is not a problem on the GPU because of its large parallelism. On the GPU, we need to optimize for data movement. And by data movement, I mean two things. First, moving large FSS keys from CPU memory to GPU memory. And second, communication. Right? So communicating across the network with a remote peer. So when we design protocols that we know are going to run on the GPU, we try to reduce this data movement as much as possible. Okay, so with these preliminaries in place, let me now tell you how we approximate the Galo activation function. Okay, so on the left, you see the analytical expression of Galo, and on the right, you see the plot of Galo. I think the plot of Galo makes it fairly evident that Galo is very close to a much simpler and also very popular activation function called ReLU, right? ReLU is a piecewise linear function which takes the value x when x is positive and is 0 otherwise. Now, because ReLU, okay, notice from the graph itself that Galo is exactly the same as ReLU everywhere except in a small region around 0, right? And inspired by this, we come up with the following approximation for Galo. Okay, first we define a function delta, which is ReLU minus Galo. So it's essentially the white line, the white space between the red line and the blue line. And then we write Galo as ReLU minus delta x. And because the red line is always above the blue line, delta x is always positive. Now, cryptographically, right, this already puts us in a very good place because we know how to compute ReLU very efficiently with a single secure comparison. The key challenge over here is computing delta. And we don't yet know what delta looks like. Unfortunately for us, delta is an extremely nonlinear function, and in order to accommodate its extreme nonlinearity, we compute delta with a lookup table. Now, lookup tables are very flexible in that they allow us to compute arbitrary functions, but at the same time, they're very expensive to compute cryptographically. And this is because in order to preserve the privacy of your input, right, in order to preserve exactly which row of the lookup table you're looking at, you need to touch every single row of the lookup table, which means computation linear in the size of the lookup table. So if your lookup table is very large, your secure protocol can get very expensive, right? So keeping this in mind, preemptively in Sigma, we design our plain text approximations to use extremely small lookup tables so that when we realize them securely, they can be realized in a very, very efficient way. Okay, fine. So with that, let me talk about how we realize delta with the lookup table. So the first observation that we make is, oh, right. So before I start, I should mention that, in contrast to plain text inference, as we already said, which happens in point, secure inference happens in fixed point, right? And for fixed point numbers, you need precision. And in Sigma, we always assume a precision of 12 for all our models. Our protocols are more generic and, will work with any precision, but for ease of exposition here, I will always either implicitly or explicitly assume that we are working with a fixed point number that has precision 12. Okay, fine. So with that, let me start. Now, because ReLU is exactly the same as, GALE is exactly the same as ReLU, almost everywhere except in a small region around 0, delta is actually 0. But delta is actually non-zero in a very small space, right? So it's 0 outside of -4, 4. Therefore, our first step is to clip x so it lies in -4 or 4. Clip or clamp, if you will. What this means is if x is very negative, then we clamp its value down to -4. And if x is very positive, then we clamp its value down to 4. And this gives us the advantage that when we create a lookup table for delta, we only need to think about values that go from -4 to 4. And for precision 12, this means around 15 bits. Okay, our second observation is that delta is even, right? And what this means is that your lookup table is storing redundant information, right? So from -4 to 4, the information your lookup table is storing is replicated in whatever it's storing from 0 to 4 and is not really needed. So in order to reduce the size of our lookup table still further, we compute the absolute value of x and then look that up in the lookup table, right? And this allows us to halve the size of our lookup table because now we only need to think about values that go from 0 to 4. And what this means is that you have a lookup table with 2 to the 14 edges. Finally, to compress our lookup table even further, we get rid of the 6 least significant bits, okay? And we only retain 6 bits of precision, and we find that this is enough to match plain text accuracy. This is enough to match plain text accuracy. So once we get rid of 6 bits, out of our 14-bit input, we are left with an 8-bit input, which is what we feed into our lookup table, right? And this is incredibly efficient to realize. Even cryptographically, it requires just 2 AES calls. Okay, so this is our plain text approximation, and this is now what we're going to realize securely. Okay, fine. So this is our plain text approximation. First, you compute ReLU, steps 2 to 5 are computing delta, and then finally, you take the difference of ReLU and delta to get GALE. Okay, so if you were to do this naively, right, just by securely computing every step of the plain text approximation piecemeal, then this is the cost that you would see, okay? But in Sigma, of course, we do better, right? Now, note here, interestingly, because your lookup table is only on 8 bits, it is not what is dominating the cost of your secure computation. It is, in fact, the comparisons that you're computing on n-bit inputs that is dominating the cost of your secure computation. And so, in order to optimize, we're going to try and reduce the cost of comparisons, right? There are 2 ways of doing this. First, just do less comparisons. And second, if you recall from the previous slide, the cost of a comparison depends linearly on the input bit width, right? It depends on the bit width of the number in which you are performing the comparison. So we're going to try and reduce that as well. Okay, so the first observation we make towards reducing the cost of comparisons is that clip steps 2 and 3, right? So clip and absolute value are in fact commutative. And what I mean by that is that it doesn't matter if you first clip x and then compute its absolute value, or if you first compute its absolute value and then clip x. Right from the point of view of the output, both these operations are the same. However, from the point of view of secure computation, it makes a difference because if you compute the absolute value of x first, then you know in your clip operation that your input is never going to be negative. So you don't care about the negative part of the clip at all, right? So you can just perform a one-sided clip. Okay, so you switch 2 and 3. And what this buys you is that instead of 2 comparisons in clip, you now just have the 1 comparison. This also buys you something else. which is that the absolute value of x can actually be computed as twice the ReLU of x minus x. Since we are anyway computing ReLU in step 1, this means that we get the absolute value of x for c. So we produce two comparisons. There are other optimizations that we can make as well. For example, step 4 requires us to perform a truncate reduce in which we get rid of the last of the 6 least significant bits of the precision. And doing this does not change the outcome of either the absolute value of x, which depends on the sign bit, has nothing to do with the precision, or clip, which depends on the integer part of x, and once again, has nothing to do with the precision. So if we perform truncate reduce first, right, we are able to perform all successive comparisons, and by that I mean comparisons in step 1 and step 3 on smaller bit rate inputs, right? And you lose, so instead of performing comparisons on n bits, you're performing comparisons on n minus 6 bits because you got rid of the last 6 bits of your precision. Okay. Finally, a final optimization comes from the domain itself, right? So GALO is an activation function, which means that it always follows a linear lag. And as Divya said, after a linear lag, you have to perform a truncation in order to recover your precision. So, so we use this to further reduce the bit width over which we perform comparisons in 1 and 3, right? Because even though you might be getting an n-bit input, you know that the value contained within that input is only going to saturate n minus f bits, right? Because the last f bits we just got rid of via truncation. Okay, so after all these steps, we now have a secure protocol for GALO that is highly compute optimized, and this compute optimized protocol runs really well on the CPU, where compute is the key constraint, right? However, recall that on the GPU, we had different constraints, right? Compute was not a problem. We cared more about key size and we cared more about communication. So while I will not describe our GPU optimized protocol for GALO, I will tell you that it makes the following trade-offs. It has a key that's twice as small, it has 30% less communication, and it has 1.5x more compute compared to the CPU version of the GALO protocol. And to show you that this trade-off is worth it, more compute for less communication and a smaller key, I will tell you that our GPU optimized version of GALO is 40% faster than if we just naively ported the CPU protocol to the GPU. Okay, so now finally I'm going to show you some numbers. I'm going to compare first our CPU version of GALO to crypt10. And here we see that crypt10 takes 20 seconds to compute GALO and GPT Neo, and Sigma running on the CPU with just 4 threads is able to match crypt10's performance. Okay, and now I will compare crypt10 to Sigma running on the GPU, and here we see that Sigma on the GPU is an order of magnitude better in terms of latency, and also is also an order of magnitude better in terms of communication. Okay, so what I've shown you is that for at least one nonlinearity, we have a very, very efficient approximation. We also have very efficient approximations for softmax and Lernom, but I don't have time to talk about them today. Please read the paper. But now it's time to show you that these efficient approximations are also accuracy preserving, right? So this table shows you that for all our models, we are able to match plain text accuracy. And, just to emphasize, this did not require any change whatsoever to the underlying model, and we didn't even retrain the model. We just used pre-trained floating point weights out of the box, and we performed secure inference. Okay, fine. So now let me talk about evaluation. So we evaluated Sigma onto A6000 GPUs in the LAN setting. And as you can see, Sigma is an order of magnitude more efficient than crypt10 in terms of latency, and it is almost an order of magnitude more efficient than crypt10 for communication as well, right? And finally, let me talk about scalability, right? So here we see that Sigma scales to models with 13 billion parameters, where crypt10 fails after 2.7 billion parameters. And also that Sigma running on the CPU is as fast as crypt10, which runs on the GPU, right? And finally, I want to conclude by saying that for the 13 billion parameter model, we are able to perform secure inference in just 44 seconds. To conclude, Sigma is the first system for secure inference of transformers, handling GPT models and scaling to tens of billions of parameters. We create novel FSS-based 2PC protocols for the complex nonlinearities that we see in transformers. And these protocols are based on plain text approximations that are efficient to realize cryptographically and are yet sufficiently precise to preserve plain text accuracy. Sigma also designs protocols that are specific to the hardware on which they are going to be run. Our code is publicly available. Please take a look. Thank you.